Hi everyone. Thanks for accommodating this request also. I'm very thankful to the NPT that this worked out. Like we have these three sessions planned in different times. So this one's 3 point. Then the one on the 18th, the time for that is 3 point. Like this for this, the day was 3 point. For that, the time is 3 point. It's like 2 3 hours early for you. And then you have the coming week, so the third week mostly the last week of this month. So I guess so since this is fourth week for us, so it would be sixth week most likely. So on the sixth week we'll do it on the Saturday and not on the Tuesday. Sorry, on the Saturday of it and not on the Tuesday of it. Okay. So yeah, I'm traveling outside. That's why I won't be able to take it on usual hours. Hence this arrangement is being taken. So, hello everyone. Let's start for today. I'm Jagriti Patel, PhD student from Biological Engineering and Sciences from IIT Gandhinagar. I work with Professor Kalamakada Shekhar in the Muse Lab, Medical Ultrasound Engineering Lab, and my research focuses on quantitative ultrasound for tissue characterization, so developing techniques through which we can, if you do have conventional ultrasound images or signal data, can you extract more information from it? Essentially, the tissue information is encoded there, but we don't see it in the great scale sonography image there. So we're developing techniques, already well established techniques, and to see how can we further improve it and give it to physicians, clinicians, diagnostics, so that they can make an early difference and hence can do their decision making and treatment outcomes early. So with that we are here for the course. We are here for the course Biomedical Instrumentation from Professor S.K. Varadan. And last time we saw in week three, I'm still trying to connect my tablet. It's not. You'll have to give me 5 minutes. But I gave you like just a quick review of what we did last time, and in 5 minutes I'll connect my tablet. Okay. We looked into the indirect. Let me open the notes here. So I believe, so yeah, I have uploaded all the lecture and assignment notes on the link and the sheets which I've shared with you. If you do have any questions, if you're not able to ask in the same session, you can always carry forward and ask me in the in consequent session that will follow. So last time we looked at somehow about we started with the heart, how systemic circulation is about. Then we went into pressure measurement. So we went into direct method of pressure measurement. Then we looked at few, we also looked at indirect pressure measurement, but we didn't go into that much deeper of it. Um, we looked at different sensors. We looked at strain gauges, linear variable differential transformer, then conductor and capacitor based. We looked at sensors, the pressure estimation sensors, which sit on the tip of the catheter, and the ones which have fluid in it. So we looked how both of them are how both of them work out, which one has which advantage and disadvantage, which will be feasible in the long run, and which type of application suits for both of them. Right. Then we looked at piezoresistive sensors. So in between piezoresistive sensors, we also had a good backup about Wheatstone bridges and how gauge factor was being defined for them. Then we looked at, okay, when designing these things, there are two design considerations that one should take. One is durability and next is stability. So for stability, it was more as that of a sensitivity factor. Okay. Then Uh, it was about the pressure estimation, and lastly, we went to we were looking about the frequency responses. I was trying to see that okay, if it's a flat frequency response, that means a broadband system, and that means that it is very sensitive at all frequencies that you are trying to look at. But instead, if you have a system where it's only specific to a single frequency, or will get excited that it's you will get excited at any transfer frequency, but resonates at only that resonant frequency, then it's very narrow band, and then it is not suitable for long-term applications, but instead real-time point of care applications will work for it. But not that, okay, if you have a patient admitted in ICU and you need to monitor him for longitudinal times, you won't be able to do that with that type of system. Okay. And then we like while looking at fluids, we look at the second order partial differential equation, and there from there we looked at how resonant frequency, damping factors, and what else was there? Viscous resistance, how these three were related to each other. So these three formulas are very important. After that, in week three, you see that where's the point? Yeah. So we had this direct point of measurement where we had the intravascular sensors, that is the one on the catheter tip. Then we have the extravascular ones, the fluid-filled ones. So we looked at both of them. And then there was this indirect method of oscillatory method or oscillometric method. Oscillometric, we looked at very briefly that how it oscillates and this resonant frequency should it correspond to. Oscillatory is like something which deals with the sound when a person listens. So that's more of an indirect method. So we'll just quickly look the main principle of it. So we looked at the Bernoulli's equation and the equation that follows it, the how energy is being conserved, right? So that's equivalent to the pressure at a point plus the static pressure at that point plus rho gs is something which tells you about the potential energy and plus half rho v square that tells you about the kinetic energy of the fluid, right? And then you can place the sensors, the catheters in like upstream direction, sideways, downstream direction. Both will give you different impacts. Like the upstream one will give you a higher reading, whereas the sideways one will be accurate because it is considered the sideways current. The downstream one will be closer to the side pressure, but it will vary because now I'm at home, that's why there is noise will come. Okay. So, and the downstream, the one which is placed at downstream, it is closer to the side, but now gravity is acting on it. So the pressure there will also vary. So it's slightly unstable. Okay. Um, then yeah, I told you that what that sphygmomanometer was, right? You have a cup, then it we fill it with air and increase the pressure, and the artery will come. So that pressure, the cup will compress our arteries wherever we are trying to measure it at in brachial or like brachial venous arteries. And then when it does that, it is now restricted. Now blood flow is not going through there. And then this, as in how we increase the cuff pressure to be, let's say, more than diastolic pressure. So more than 120 mmHg. And then we use the pressure. So it's within the systolic and diastolic 80 and 120. And then after a point, it's very less than 80 mmHg. So within this cycle, what you hear is when your sound disappears and when the sound starts appearing. So what doctors will hear or they will, MD physician will hear is that what was the time point where he like where the sound was not visible to him or was not audible to him, and he'll look at the pressure levels at which particular pressure am I at where the sound disappeared. So now it's not the time here, but it's that the pressure that we're trying to measure. And then he'll again cuff it and then he'll see. Now there are different reference points to measure this also. So we have like you have some reference sternum line at the fourth intercostal muscle. We also have at the back. So there are reference points for which you look at, and other points where the blood flow measurement won't impact that much to your pressure measurement. Okay. So that was more about this auscultation method, and we looked at different frequency ranges. So systolic will occur more in the 20 to 30 hertz regime, whereas diastolic will occur more than that. So you can take it as 40 to 60. So that's 10. So that's and then it is the next one. So we also saw when we began with the mean arterial pressure, right? So what it was that it was like one third of your yeah. So it was your one third of systolic plus two third of diastolic pressure. Or else you can also tell it as one third of your systolic. Hmm. Yes, it's systolic. So one third of systolic, it can be a systolic plus one third of your pulse pressure. What pulse pressure here is your systolic minus your diastolic pressure. So this is diastolic plus one third of pulse pressure. So diastolic, and then you have one third of systolic. So one minus one third, that becomes two. Okay. Yeah. And the sounds that you're hearing, so something where your blood pressure sounds the in the auscultation method, those were like correct sounds, right? So in the first point where you hear it, it's a disappearance point. Then later, so there's a curve which decreases along with pressure, and you hear the sounds. Those sounds are nothing but and then when your blood is passing to the heart, from which chamber to chamber is it going to? So these are nothing but closing and opening of the valves. Right. So there are like a total of five for sounds. not writing, I'm not able to connect. I guess I'll take a 5 minute break and then connect it. In the meantime, we'll just go. We'll complete the week three and then when we go to week four, I'll try and connect this again. Okay. So yes, like there was your first corrective sound is a snapping sound, which is like first heard at the systolic pressure. So when you're trying to compress it, so when everything collapses, your artery collapses, you're not able to hear anything. So that's something that you'll hear a tap like that sound. So the sound is something as kind of loved up, and like those are the sounds where your heart was makes, but something in pressure is also similar. Okay. Second sounds are mostly the murmurs in between your systolic pressure and diastolic pressure because now your pressure ranges in between 120 and 80 mmHg. Third is a very loud and crisp sound. Like you will see that okay, the blood has started to gush through it and hence it's being flown to the arteries. And fourth is a point where it's tongue. So it's muted. You don't see anything. So that's the disappearance of that. Fifth is where your pressure it's complete silence. It will drop below the diastolic blood pressure band. So the second one and the third one, so far, they don't have any clinical significance. Might be related to something which is not like can be an anomaly or in a disease condition like that. But till now, what doctors will hear is the first sound and the fifth sound. At times, they'll also look at the fourth sound. We'll try and find what the difference in between the fourth and fifth sound but not really into the second and third because that's like okay they know that this is a molecule now blood is starting to gush through and the third one is like third one is like okay now it has completely starting to into that. Okay, so that was about this auscultation method and how to display it, where you place the cuff, which artery, which fossa are you taking it look at. But it's mostly at the brachial artery. So that's very good. So that is where pressure measurements are usually done. Either it's invasive or non-invasive measurement. Um, yes. Then we looked at oscillometric pressure measurements. Oh, now everyone knows about mean arterial pressure, right? And then the okay. Yeah. Yeah, and then afterwards we didn't actually look at the body temperature measurement, but we had a look on it before it that we had, like, we looked at the working principles of thermistor and thermocouple, how one was flat, how one can be used, how one measured the surface temperature, like both measure surface temperature, but one can be made invasive. One tells you about absolute temperature measurement, the thermistor, whereas thermocouple will give you a relative measurement. And then like which principle it works on is like thermocouple goes from Peltier limit. So what it will see is like the difference in temperature or the current voltage in between the two notches or two junctions of any two different metals. So heat is either absorbed or then released at the junction, which is how directly it is proportional to the temperature differences. Okay. That's how I remember till now. If it's something else, I can always look at it and will let you know if there's something extra. Then, like you can have a look at which type of material the thermistor and thermocouple is made up of, like which is mostly preferred material. You can say like two conditions. One can be either real-time and point of care, and second can be how longitudinally monitored, like in which cases which material can sustain for hours. So that thing can also be. Okay. Mine will reference that one is related on the negative temperature coefficient, whereas the other one is directly proportional to the change in temperature, so it increases. So similar to how your wavelength changes in the optical sensors that we look. Okay, so that was all about week three. Then week four will be dealing with measurement of flow and volume. So once we looked at pressure, after pressure, so pressure incorporates a term of flow. Because of that flow, you see a disappearance or presence of the blood in your artery, right? And that is what we are trying to measure. Now, at which velocity or at which speed it is traveling through, that is a point which tells us about the flow. And in what cross-section area is the point which tells us about the volume of it. Okay. So give me 5 minutes. I'll try connecting to the system. I guess it's the thinking issue. So I have a one-day connected, right, where all the materials are shared. Uh, with the space I have last week, some recording also stored here, so it's not able to repeat it. Uh, It's not allowing me to share my thanks for even really because it's already uploaded on. That was talking just talking. I'm not able to follow back the session was having. Today also for 9 hours, and we are looking at week 4. Let me know if you're not able to read it. I'll zoom it further. If this man has tried to be within the page limit, is this visible to you? Or else I'll try writing in simple form. Okay, I hope this is visible. To saying like even if you don't understand a point of thing, you always have the lecture notes with you and you can directly download them and zoom it and look at them. I suggest you look more closely at the lecture material which is being provided at the SWAM or NPTEL portal. And then on the slides when you try and understand them, then you can make the notes. You can take these notes also, you can make your own notes also. That's the way you can learn more efficiently. Okay. So we'll begin with measurement of flow and volume for this week. Well, there are multiple variety in this week also. Like I haven't seen a course which provides this much deviation, like this much in number of topics in the first in 1 week itself. But it's good to have something like that so that you always have an idea what you are trying to look at. So here, like since last time it was more about the pressures, everything went on pressure. Now, but this time it's also flow, it's also volume, it's also temperature that we'll be looking at. Okay. So, if you remember how I told you how heart works, and we have been talking about it quite like from week 1 onwards. So, like you have 4 chambers to it, and you have different arteries and veins which take it to lung for oxygenation, deoxygenation. Then you have your heart's real pacemaker, your SE node, sinusoidal node, then you have your AV node, atrioventricular node, and it goes on further. You have a physical activity, mechanical activity of heart, and you also have an electrical activity of heart. Both of them really do the same thing, but occur in the different fashion. And how you measure the entire flow, entire volume through it, how much time it took to pass the blood once it was injected into your heart from the entire body, and then to release it from the heart for systemic circulation. So that's what defines your cardiac output. Okay. So now from where this flow comes, sorry, it's happening. From where this flow comes. So what is flow? You all know. So this is movement of blood. Right. I hope this is visible. So I have a feedback for myself, but it's not if it's like if you're attending to any other device, let's say a phone or tab, and if it's not visible to you, you can always let me know. I'll try and zoom. Okay. So it's a flow movement of blood through a vessel, can be a tissue, can be a organ. Okay. So this is nothing but n number of them make this, n number of them make this. Okay. All are nothing but cells, arrangements, walls, tissues. Okay. So now, how do you measure volume? What's volume? So sorry. What's flow? Again, we don't go into one there. So what's flow? It is volume of blood that is flowing through a vessel, tissue, and organ per time. How much blood is moving with respect to the time per time that we are looking at. Now, how it's difficult to measure or where it's difficult to measure, if because let's say I do a minus sign for it or a cross sign for it in microvasculature. We need advanced signal processing based methods to do so, or we need directly invasive sensor at point of care to where we are trying to measure. Using indirect measurements of flow, we cannot measure it. And what I'm talking about is something in the order of microns, is something in the order of which is like less than 2 centimeters and can also range from thousands of mm. So this is the range that I'm talking about here. So microvasculature essentially. Okay. And then if within the arteries, like you do see branched arteries, then you do see multiple arteries connected in a point, right? You do see this fragmented arteries like this. So there are many of them. And because of this, the blood flow which is occurring from here, so of course you know that this one end would be thicker. Like just remember from your basic fluid dynamics or mechanics if you have learned previously. What happens is the one which has a larger diameter will have more blood flow volume or blood flow through there. So the volume is also high. But soon it starts to like differentiate or bifurcate. It is the point where the velocity also halves in it, right? And since it decreases, then here also decreases. So there are different range of flow velocity. Okay, so when this is the case, you won't actually know what was the true velocity at that particular point where you were trying to measure. And now you won't have any ground truth to measure it. It's just the known physical knowledge or the literature that you have to improve. Okay, and then hence you need so that's motivation for learning this thing. You need a very sensitive, accurate, and a stable sensor, right? So this is the thing that you need. Now, what are the different types for it? We'll just make a flow chart quickly. Take types of flow measurement. Okay. So what they are? Can so the first one is electromagnetic Like all of them are flow meters. Let's just say this flow meter is FM. Electromagnetic flow meter. Then you have some based on ultrasonic. Okay? Ultrasonic flow meter has something like Doppler based method, transient based method. Okay, so it works on the shift of frequency. So one is transient time, right? One is continuous wave. You keep on measuring it. One is pulse wave, and one is laser wave. Okay, so you have like transient time, continuous one, pulse one, and laser based. Okay, so that's different also. And then you have thermal based. Based on temperature differences, you can also get an idea about the what is the flow of blood through that system at that point. I guess this is it. Yeah. So first we'll go into the electromagnetic flow meter. This works. Let's see if we can write in fashion. So you have electromagnetic flow meter. So what happens on this? This works on Faraday's law. Any one of you here remember what Faraday's laws are about? Let's like you can just tell me what quantity it deals with. Electromagnetic induction. Okay, EMI. So which particular what does it say? Which particular physical parameter does Faraday's law of EMI work with? What are we trying to look at there, and what differences let us know about the flow through there? What are we picking up? Like we have studied this multiple time, and everything leads to one quantity itself, which is then converted and then saved and then further the process on it. What is that quantity? Okay, so that's voltage. Okay. Essentially, whenever you try and look at something, the output will always be a voltage signal. And now in this case, we're looking at Faraday's. So you have an electromagnetic flow meter. So this flow meter, the name of it tells you that it is dealing with something as magnetic quantity. Then magnetic quantity will convert into voltage. Okay. Now what was Faraday's law? The was for it. Go have a look on it. It's very like you should know what Faraday's law are about and what it deals with. Okay. So this one works on Faraday's law of electromagnetic induction. What happens here is the blood is flowing through it, right? And how blood flows through an artery or a vessel. In electrical terminology, what else flows? Through a resistor. What else flows? When we apply a dash flows. Often the resistance tries to oppose it, and hence we see a voltage difference. What flows? What is an equivalent quantity here? Ohm's law. So yeah, like that was unhinted. So what's an equivalent quantity? And current, right? So here, when our blood is also flowing, this acts as a conductor. It allows to pass it. Then, due to the blood flow, there is a voltage which is being induced. Now, since the voltage is being induced, so this acts as a conductor, and this voltage will get induced when the blood is flowing through it, right? So, how it flows through it? Now, what is your trans excitation here? Excitation source? Is it electrical or magnetic? The magnetic. Okay. When you apply a magnetic field, Okay, when you do so through a coil, when a magnetic field is being applied, so that is usually represented by blue. So when this is usually applied, and then a blood is flowing through it, there happens changes. Now, what those changes are proportional to, how do the changes are proportional to, it's Faraday's law. We will look at it, okay? And then what gets induced is nothing but the voltage through it. The voltage is being induced, right? So there are different just flow meter sensors. These are very small. You can have it attached at the two ends of the tubes where you're trying to measure the flow. Okay, but it's very difficult to do this in real scenario, real basement. So what happens is your magnetic field is then placed at right angle to the vessel. So it's here. So it's directly placed perpendicular to it. The blood flow will create a voltage, and the electrodes which are being placed there at the end of this two sensors, where you're trying to connect the heart key, they will pick these electrons. They will pick up this voltage, and hence we'll try to measure the voltage. So the voltage that's being produced is proportional to V, the velocity of blood flow, and the diameter of artery where you're trying to look at. Okay, so this and the time people also say, or in your 11th grade textbooks, you might have also seen it as BLV. That's something as blue what I learned when I was doing my 11th grade physics. Okay, so this is your voltage, this is your magnetic field, this is your velocity, and this is your diameter of artery, or yeah, wherever you're trying to look at. Now, this also has its own industrial application, has been used in multiple bigger boilers based system where you want to see that how much fluid that you have placed and how much it is being flowing from one point to another point. So people also use this in industrial based application. So in this case, this is velocity and this is diameter. Okay, so the length of it. But people get confused, like they consider length as this length, but it's not the length that you're trying to consider. Hence, it's more logical to use this one because it essentially has a bead in it, so you'll eventually use a diameter there. Okay. And then how flow, so how your velocity and area are related. So when you want to try to find, so how much flow is being going through that artery with respect to unit time or unit area. So it's nothing but what you call it as flow rate, right? So this is Q, what you call it as flow rate. So this is given as velocity of blood flow through an across a unit cross sectional area time where you're trying to look at, right? This that's the formula only. Okay. Did I write it wrong? Flow rate. That flow rate is represented by Q. And okay. So that's the velocity of the blood flow through a unit cross-sectional area, not across it. Or else, if you want to find velocity from here, so that can be given as the flow rate given cross-sectional area. Okay, so that's the exact quantity. Sorry for confusion. And this is the velocity, and this is the E, right? Of let's say the vessel can be a conductor. Okay, these are the things that you have in there. Then, um, you can So you have these relationships. What if you try and input it here? So you have a velocity component there also, right? So you see E is equals to you have V and then you have Q by A times your velocity that you have in here. Right? Sorry. We substituted velocity, so that's diameter, right? So this is diameter. And now what is area? Area is pi r square. What is diameter? Sorry. Area is pi r square. So, I'm sorry. How can we write this radius? We can also write radius as b by 2 of square. So we can also write it as pi b square by 4, right? So how do you write this? This can be given as E is equals to b q, you have b by pi b square and 4 goes on top, right? We have 4 b q by pi, and then you have a group here. So this is very complicated. What you do is you just remember this one, or this is much more easier. So like either the flow rate through so velocity times area, or the velocity is how much flow rate is there across the cross-sectional unit area. If you want this is as more intuitive, and this you need to know that electric field how it's being induced or voltage how it's induced due to the application of the electric field across the vessel that you are trying to measure at. Due to an application of it across the vessel that you are trying to measure, so the diameter of the vessel times the velocity of the blood which is being flowing through it. So that is how you get induced. Because now blood flow acts as a conductive field. So acts as a current there. Okay. And how they are being designed, so they are magnetic, right? So they have a magnetic part and a non-magnetic part. The non-magnetic part, that is the tube, the outside one, because you don't want it to be also interacting with the core, which is magnetic, and you have multiple coils being like turned or coiled around them. So you don't want it to interact with it. So that tube is non-magnetic and it's lined with insulation. You have different electrodes for this type of sensors, right? And a little bit of space down here. We have different electrodes. And these electrodes can be stainless steel or platinum. Okay. Can be stainless steel or platinum. The differences in between types of them varies based on the type of application that measure it at. If it's a bigger artery, if it's a smaller one, what the diameter of the artery, accordingly it will change, right? So the inner iron core that you're trying to pay is that it will be polyimide, usually less than 8 mm. There is the one, the outer core, which is like air core, which is insulated from it. It's like more than that. Okay, so this is for inline based applications where you have a smaller point of time where you're trying to measure. Okay. Now there are also different types for this electromagnetic sensors, electromagnetic flow meters. One is your sine wave, and the second one is your square wave, right? So now for the sine wave ones, for the sine wave ones, first, like since it's telling about sine wave, what it does is we'll send an alternating current, an AC current field. So we of course to induce a voltage difference, you when you apply a magnetic field and there's some current passing through it, so there's a flow passing through it, you will have a phenomenon of induction there, right? So you use an alternating current wave to generate this magnetic field. Also, since you try and say send this current wave or you have something into the conductor, those magnets will start interacting, hence it will create a magnetic field. That magnetic field then will induce a voltage at those two different points where you're trying to measure it at. And like induced artificial voltage, which RC factor voltage or transformer voltage you have, is the one that will give you the yield across the 2 points that you're trying to measure the voltage. Okay. So in this type, since it's only the one variable that you're trying to change at a point, the drift is very low and you have a good signal to noise ratio, right? It's also, but when you try and look at it for longer time, longer lengths, so the phase of it is not stable. What I mean so stable is because sine wave is an alternating current wave, so it's an AC wave. So what it will have is it will also have it so how you write it as can be. Do you remember Euler's law? Right? So you have a magnitude assigned with it, and you also have a phase assigned with it. Now these two components are the ones which see that how was the amplitude of the wave, how much time it will repeat, what's the periodicity of it, those things which are there. So because of it, the phase stability is will have some constants on it, right? So the transformer voltage that we just talked about, it will cause an baseline drift because it's the initial point, but we can also eliminate it using an amplifier or the filter there. So what are the good points for it? It's highly accurate. You can do bidirectional measurements there, of course, in both of them. And you have a wide range. Now, why wide range? What is sine? Sinusoidal pulse, right? Now, what is the Fourier transform of a sine pulse? It's an impulse, right? What's an impulse? What's an impulse? The sine wave, essentially, when it starts, it will have like these two phases, right? So it has a positive cycle and negative cycle. So you'll have two impulses associated with it. If you're trying to look at only a positive direction, you'll have the one. Now, this impulse is something which incorporates or has all frequency components on it, right? So when one can also say that we represent an impulse as a combination of multiple frequencies. And when you convert this back and forth, of course, right? Frequency domain to time domain, one and the other is important. So hence its broadband has a wide range of frequencies that it is sensitive on, right? So that's all about this electromagnetic and sine wave sensor, right? Sine wave flow meter. Then there was the square wave one. So same thing, same phenomenon. So you have an alternating square wave. Now for this, your task is to go find what's the Fourier transform of the square wave. I can tell you one thing for sure. It's a sink like this, okay? A sink, right? But what you need to find now is that why do we see these things? Okay. So since in here we didn't have it was an impulse, so that's a broad range. So it has all frequencies incorporated in it, and it's only one at the point at the frequency that you're trying to measure it at. But a sink, when you convert a square wave to Fourier transform, has these two lobes across. What are those being called? And these are the ones which will cause you differences. Hence, people prefer alternating current sign. Now, I do think so that we don't have enough space here. We have a space crunch. Let's go below. Copy paste this one. No, I guess it's fine. So then we look at the ultrasonic ones. Okay. Of course, ultrasonic blood flow sensors, flow meters. What happens is we use high frequency sound waves, and because of this, how so let's just imagine. So you might have learned about Doppler in your like during a few times, right? So what you see over there. So if something is going away from me, I won't be able to hear that voice, right? That or like that frequency won't be audible to me anymore. But if someone is coming near to me, that would be audible to me. Now this is something which is related. Now, where I was standing in a straight position, I was stacked. Now, what if I also start moving? Now, I'm also moving in the same direction as that of the source of which is producing the sound is also moving. So now for me, there would be no differences and the difference is cancelled out and I'm able to hear everything now. Now, what if I'm moving in the other direction and the source of sound is moving on the other direction? Now, somehow it starts diminishing, right? Now, what if it's moving in the other direction? I'm also moving apart from it. Now, it's also diminishing. There are like these cases, and this is all related, okay? So you use high frequency sound wave, and what the difference in the frequencies occur when you're trying to measure it is what tells you about the Doppler shift, the shift frequency, and that shift frequency tells you about the blood flow velocity flow, right? So you use sound waves, you use an ultrasonic sensor, and that principle is what which is based on Doppler. Thank you. That is based on Doppler, right? This type of measurement, it is non-invasive. And it is a real-time measurement. The non-invasive real-time measurement. What it will help us do is we'll measure flow, so blood flow essentially in arteries, veins. Now you know there are two types of arteries. One is carotid and one is coronary. So we often try and make mistakes in between both of them, but these are two essential arteries for us, and which sends blood in two different directions in two different places. So see what are the differences mixes in between both of them. It's really fine. But at point, what will happen is if someone asks you where's the carotid artery, where's the coronary artery, you won't know and you will confuse between both of them. This is what I've seen over time. Okay. Even my batchmates do the same thing. So which are from electrical engineering, but do have what do you say like a biomed background or working in a biomed lab. So they do these things more often time. Okay. So what here happens is, let's say we'll have a schematic. Let's say you have a vessel. Okay. So not this part. Okay, you have a vessel. Then you have, let's say, multiple red blood cells here, right? So then what I'll do is I have this ultrasound transducer. So I told you transducer STDR, right? What it will do is, so let's say I'm sending a frequency, exciting it using F naught, and then whatever happens, it will scatter back, right? Either it will get incident, it will get reflected, like it will get reflected in the other direction, will get absorbed here, will also get propagated farther away. So it will have multiple reflections too. Right, so but in our body, we are made up of water, right? So you have more water percentage, so there's a chance that it will get absorbed in there, it will get accumulated from there. But if it does occurs through any surface changes, so if there are some changes where you have difference in tissue interferences, difference in tissue impedances, which is the right term for it, and that is how due to that acoustic impedance you see a reflection next to it, right? So then for simplicity sake, we'll do that. Okay, we are receiving it back. Okay, so that can be your, let's say, FR for receiving it back. So this is how basic Doppler principle works too. And depending on where is the velocity of blood flow, is it upstream, is it downstream, those things will vary. Now, this is what you might have learned in this time. So, this type of flow meters are two types. One is Doppler shift base. The base is one, right? So, where just now what we talked about the example where if I'm standing statically or dynamically and how is the source of sound moving against me, or it can be transit transient time. Okay, so very quickly at that particular point of time. Okay, so let's take a break of 5 minutes. I'll also get water, and then we'll start from the operation. Okay. So often speaking, this much time for late causes my throat to When having honey water. There will be, I guess we still have 2 more minutes.
Hello.
Okay, let's begin. So, doctor, it has been already used in clinics. Okay, what you see is that there are people with asthma people. So, when you go for a routine ultrasound checks screening, you do have a conventional sonography routine done, and afterwards they'll also do your Doppler imaging. We'll see if your blood flow is falling properly or not, if you have any newly developed cyst or you have any clots in there. So that is how your blood flow changes and different velocities will give them in real time understanding that where is anomaly being there. Because like if you have a what happened, someone changed the spoken language here, Estonian, and I'm speaking English. Like I didn't give any access. I was like this. I like keeping it restricted and verified, but it wasn't working out for people to see. I hope so. The recording does not change. Please don't change. Who is changing this? Now it's changed to English again. Please don't play with this. This is not a point to play with this. Okay. I won't be able to take another session if I've exceeded this session. I am already past that. Please don't change the language. If you do this again, I'll have to remove you from the meeting. Thank you. Thank you so much. Okay. Where were we? Yeah, so it's already used in clinics. We work with what happens is we send ultrasound signals way. And what I told you is like what might happen to the echo, it might get absorbed, might get reflected, might get doubled, and then we'll get it back. We get a reflection only in the cases where you have a tissue boundary or you see differences in interference. So that is how Doppler occurs, that you have a change in frequencies with respect to the blood flow. So this frequency shift, this frequency shift will tell us about the blood flow, speed, and direction, right? So it tells us about one scalar quantity and one vector quantity. Okay. So it gives us two things at a time. So it's only telling us about the speed, not the velocity, and the direction. From there, you can also derive the velocity through it. So based on upstream downstream effects, you might have done this earlier in your class 12 physics or 11th physics. You have this formula that your frequency shift is equals to 2v cos theta F by your C, right? Where C is the speed of sound, where C is very, very, very greater than U, or you can say it as V, and V is the blood flow speed in that particular vessel. Cos theta is nothing but the angle at which your transducer was kept related to your vessel where you're trying to measure it. So that's this theta. So if it's not visible to you, this is the angle from the vessel, so that's theta. Okay. And then if it's your source frequency, the frequency that you're trying to excite to your ultrasound through for measuring the frequency shift. Okay. So what happens is like what will you do in this cases? You will take two components. So let's say you have a transducer in place and I have my vessel. You will take two components along it. You will take a x component and a y, so it's just a cos component and of course it's sine component there. You'll try to measure the upstream and downstream velocity. You take differences, you'll get this formula. Okay. So there is a direct relationship that your Doppler shift frequency with respect to your excitation frequency is related to. So your Doppler shift is proportional to your blood flow speed, right? And excitation frequency is proportional to your speed of sound, right? That's your target velocity that you will that you want to find. So if you add them in two directions, this will always give you something as 2u plus you do c plus u. But now you know that this is much higher, so it will approximately 2u by c. Okay. So in many cases, this is like on the order of 1.5 meter per second or something, where the speed of sound is like 1500 meter per second, and it differs from the type of tissue that you're trying to measure your speed. Okay. So this is like how simple mechanism of how your Doppler flow occurs. And then, so what should be done in this case? Or what are the problems or hurdles you face? Okay, so this angle estimation, this theta, how much your transducer is being placed from your vessel that you're trying to measure it at, you need a precise measurement for it. And for it, instruments known as um, goniometers. Like, please check if the go over this. Goniometer. Something is goniometer. So this helps you tell you about the angle in between the two directions. And it's also been like at times it's embedded in our phones. Okay, so you tilt it, do something else, you run with it. So it has an accelerometer and it also measures the angle. So with respect to the ground level, it's trying to measure which level it is at. Whenever you have this network towers, right? So for them also, what point it is placed at, which place it is kept at, it's highly like very sensitive to that. Like in places where you do not have a network, what you do is like you go and you move your phone to one another place. So that is how you also look at it. So that the precise location and the precise point, the precise measurement device for this should be known for your measuring your blood flow velocity using Doppler methods. Doppler signal will be equal to zero when. So when will you have a Doppler velocity as zero? Looking at this formula, can you tell me that when will I get the differences in between this would be zero or differences in between these two would be zero? When would that case occur? It is something to deal with when the transducer is placed at relative to your risk. Any guesses? Like we have 30 minutes more, and afterwards we'll go to the assignment. So I guess we'll be able to complete this thing into flow meters. I don't know if we can go into the pressure, sorry, into the temperature ones. We will be able to complete the entire blood flow meters. That's for sure. I can tell you. Assignment has the equal contribution of all of them this time. So I guess for solving the assignment, you'll have to go through the other other measurement, sorry, other temperature measurement devices also. Okay. So, well, but no one's saying anything. I'll tell you. So this is based on of this cos theta. Okay. So if your cos theta is zero, when this is zero, you have theta as 90, right? So what this would be the case, where let's say you have a vessel, sorry, and if your transducer is placed directly, if it is placed directly on top of it, you know, the upstream or downstream effect, which is essentially canceling out each other, right? So the echo that you're getting back, it's your transducer is not sensing it from other direction. Now, of course, it will do when the geometry of the transducer is different. Okay, so here the type of transducer that I'm looking at is a linear. I'll tell you. So hence it's very constant, right? If it's a phase delta or a curvilinear for both of them, you'll be able to measure it. But one thing is for sure that you'll get losses due to diffraction. What diffraction is, your sound waves will bend, and then because of it, you won't be able to estimate it rightly because now you don't have information about the angle, since also you're placing it at perpendicular to the vessel flow. Now your other elements are receiving the signal back, but not the ones which are directly sending the frequency, which are more closer to the vessel than to the side plates. Okay. Yeah, of course, here when you do this, when you look a big, I wanted to tell you that your flow velocity is always highest in the center, whereas it decreases towards the vessel wall. So it follows more as a Gaussian spectrum. Okay, whenever you have this and whenever you try and estimate the flow velocity curve. Yeah. So this is about Doppler. The shift will cause the angle, the shift will cause the position to change, and hence will modify the angle through it that you're trying to measure. You don't have a shift, or you'll have a minimal shift when the probe is positioned at 90 degrees. How? Because it always depends on the type of transducer or probe that you're trying to measure it at. Okay, so this was about Doppler measurement, Doppler flow shift measurement. Then the next is, oh, I kept saying transient. It's not transient, it's transit. Like now I sign my notes, it's transit, and let's also change it here. Should be transient. I've never heard transit. Might be the same terminology, different types, how we approach things. Now, what you see in transit time flow meters is it's also based on the differences in between the ultrasonic pulses with and without. So it's a travel time on them. So one thing I forgot to tell you that why this two occurs. Like okay, in this case, what we do is like upstream downstream effect. But what happens? So I have only one probe here, right? So this is very important phenomenon. I have one probe. I'm sending my pulse through it and I'm receiving it back through. So what happens? What's the effective path length here? It is two, right? Like two times the distance it is traveling. Because when it traveled D, then it traveled D, so it's a two times distance. Why can't it be cancelled out? Because this is the transmit frequency I'm telling you, this is the reflected one. The reflected one incurs some losses. And due to those losses, these both terms are different. So my path length is effectively two times. Now what if I have one probe here and one probe here? Now this is sending and this directly is receiving. So this is my partner D. Okay, it's not two times of D. So in this case, that would be my partner. So if someone tells you and asks you that okay, get this Doppler something this, I want to try and measure the velocity against it or flow rate against it. Always keep in mind that are you using one probe? Are you using two probes? Okay, so in this case, when you see if you want to find the effective distance through it, right? Or let's say if you want to find the time of arrival, this is one of the questions which usually occurs. Time of arrival. So time of arrival of the ultrasound wave or the backscattered echo to the transducer back when the time when it will return back to the probe. can be given as 2d by c, right? Why 2d by c? What is your velocity? Like c is your velocity, right? Sound. How is it being defined? It's defined as distance by time, right? So your time of arrival can be d by c, right? Now in this case, we want a two-time partner thrown in such like this. Now in this case, the time of arrival would be directly d by c because it's only traveling to one time, right? So these are the two types of geometries which are also possible where your probe is being kept. Okay, so the time it takes to travel from one, let's say from point A to B is a downstream effect, from point B to A is an upstream effect. And the transit time is nothing but the distance is directly associated with the flow velocity. Okay, so this is the simplest thing that I would say. Now, the velocity which is transferred from, let's say, if I have two transducer in this case, from transducer A to transducer B, can be like if it's at a component, I'll directly take a component of it across the adjacent direction plus C. When it's again coming up back to me where my transducer is being placed, this would be my C minus U cos theta. Because now this is the component of velocity that I'm trying to look at. So these are your velocities. Do the same calculation, you'll be able to find the time of arrival. So it's similar. So it is 2 times u times the distance that you're traveling times you cos theta by you have a c square. Okay, so this is the transit time which takes you to travel where you have a blood flow in a velocity in an artery of length or via L, and where your transducer is placed at an angle with respect to your vessel that you're trying to move, and C as your sound speed, speed of light, sound speed or speed of light. So it again depends on the type of sensor. Either you are using light, either you are using sound. This will vary in those cases. Okay. Now next one is pulsed wave Doppler. Now what happens in pulse wave Doppler? So you might have heard. So there are always these two things, right? Analog, digital. Analog is continuous, digital is discrete, right? The digital will have some duty cycle. Digital will have some pulse repetition frequency to it. So these are like some technical terms about if you send a pulse in two times, you have duty cycle. What's that? It's like the time where your pulse is on, whereas the time of your entire pulse duration that you're trying to look at. Okay, whereas continuous is like it's continuously doing in varying spatial and temporal domains, right? So here also you have two things. One is your pulse wave and then is your continuous mode. Continuous is what we have been looking till now. And pulsed is, well, like will change over time like this. Okay, so let's say if this is 20 on, this is 20 off, I'm looking at this period, right? Period T. So my duty cycle can be given as T on by T on plus T off. Okay. So let me know at any point if you feel that the session is going too slowly. I can also speed it up. But I was given this feedback when it was last time I had a session that sometimes people weren't able to follow back, so they had to reduce and hence the session also ended quickly. But I'm trying to reduce it, but we have too much content. That's a problem. My speech would also be very fast, but writing takes some time for me. So if you're able to follow in this time, works well for both of us. If not, let me know through your feedback forms or on the online sessions also by raising hand, by unmuting yourself, that what needs to be changed, I can do. Okay. Yeah, so for pulse wave Doppler, so what for continuous flow meters, you don't have a profile detail. You don't look because it's continuously being sent, continuously being received. Whereas what happens for your pulse wave Doppler is what you're trying to look at different depths using your delayed echo. So you send echoes at different times. Now the one which has a higher frequency. Okay, so you know there's always a trade-off in between frequency and wavelength, right? How they're related, C is equals to F lambda, right? So you can measure C as this like this, right? So now this increases, this decreases. If this decreases, this increases, right? So there's always a trade-off in between wavelength and frequency. Wavelength, you can take it as depth of penetration also, like how much it is being traveling back. So it's the same formula as that of your time, distance, and velocity. Okay. So the lower the frequency, the more it will penetrate, the deeper it will penetrate. The higher the frequency, the shallower it will be. Right? because it will be attenuated faster. And the higher the frequency, the more resolved factors you see in your ultrasound wave. So you have a higher resolution. Whereas the lower the frequency, it's been traveling across depth, so you don't have enough resolution there. So the resolution degrades in that one. Okay. So what happens here is a brief ultrasound wave is then is transmitted. You see reflected echoes, which are then received through a time delay, and that time delay will tell you information about the depth it has traveled in your tissue. This echoes will further help us build the velocity profile across the blood vessels. Now there are trade-offs. So you see, same thing. This one with respect to resolution and depth that you're trying to follow is different. But in case of pulse, wave Doppler, there are trade-offs. Let's say if you use a short pulse, okay? If you use a short pulse, you have a better range resolution. So now this is no longer in terms of frequency, but this is the duration of your pulse, okay? So you have a short pulse being seen. So at times using your short pulse with respect to different position of time, now have a better range resolution. You'll be able to resolve that range, the depth you're trying to look at very nicely. Whereas if you have a long pulse, you'll have a better SNR because now over time I'm sending this pulse, even if it's in between duty cycles, I'm sending it. So now it's receiving completely. So I have a better SNR and my velocity I'll be also able to discriminate nice. And velocity, let's say, and velocity estimation. So you have a better SNR and better velocity estimation in this case. Okay, so there are two cases which are being based on this pulse repetition period or rate. What is pulse repetition period? Let's I we talked, right? We have this pulse. Now, after how much time will this pulse repeat it itself? So the rate is nothing but with respect to frequency. Period is something with respect to time, right? So if I talk about pulse repetition rate is the frequency I'm talking about. So now this is related. It should be less than 3 by 2 times you have RM. So this is the range where you're trying to look at, the useful range. Why it's 2? Because we're only talking about one probe for now. So you're sending and receiving back. So this is what we derived here. Right? Okay. Okay. So now if you are aware with Shannon-Nyquist theorem, so if you are aware with this theorem, you see that the maximum velocity or frequency, if you want to try and detect, should be 2 times of, oh sorry, the one that you can discern should be 2 times of the maximum frequency, or it should be more than that one. So that is what Nyquist theorem tells us. So this is about sampling. And this sampling is related to how quickly discern you can estimate your range and velocity from there. Right? So in this case also, the one should be higher than that of 2 times of Doppler shift frequency that you're trying to measure. And if you combine this and this, right? So what you'll get is you have your velocity times, let's say, a cos theta, because now also I'm inputting the value of f from my flow shift, so this Doppler shift formula is also coming in here, times your range max should be less than your c square by 8 times c square. So in trying and derive, you'll get the exact formula. I did by myself, but I don't know if we'll have continuity if we start from here. So this is pretty simple. You don't need to memorize it. What you need to know is the sampling theorem. Multiplication frequency is also fine because now you saw it here, right? How you can see their formula, the time of arrival has been calculated. So this is basically the same. So these are the two things where you need to avoid it, and you should be less or less, more than that, so that you will avoid what if you're not sampled enough, you'll get into aliasing. So that is loss. Okay, so that is what will occur. The last one is laser Doppler flooding. Okay, 2 minutes. Huh? Now, for laser Doppler flow meter, it's basically the term that's standing in front of it. So your excitation source is now light. What you're receiving it back is also light. Now, light is being transmitted. Light is being scattered through your moving or shifting red blood cells. And now you're changing the change in frequency shifts, as in how your light scatters, changes, shifts, or moves. Okay. Now for light, you have different ranges of light. Right? You have different variants at which your light can be absorbed and scattered, can be detected. You have a mono. If you have a monochromatic beam, a single wavelength beam into your tissue or skin, it will get scattered. Right, and the one which is directly sensitive to it will get inserted. Okay, the light which is scattered by the stationary structure will get unchanged. The light which is scattered by the moving red blood cells will undergo a frequency shift, and that frequency shift is directly proportional to what velocity. It's the same. So it's non-invasive. It's also real time. It's very sensitive. It's safe. It's painless. Costly. Difficult to handle. It's also complex. Right? That's why people prefer more of ultrasound-based systems than of laser-based systems. Of course, laser, since it has a very sharp, precise beam, the spatial resolution is very nice there, it's very higher. Because of that, it's very good for applications as superficial. Okay, so you can measure it as 5 mm resolution scale. You can talk about it. But ultrasound, on the other hand, it lacks on resolution with respect to this laser-based system. What they'll do is like they'll work on depth, will also give you a good resolution. But if you follow within this aliasing, if you sample enough your content, don't run up into aliasing, you'll get a better range ambiguity there, or better range estimation there, won't no ambiguity. But your resolution might be the case where you'll get a trade. That's why now what people do is like they use photo posting. Okay, so what they do is like they'll transmit or excite your source or the subject through light, and then what the acoustic energy is being created there, they'll receive it through like piezo sensors, okay, which will convert that mechanical form of energy into electrical energy. And so that's a combination of photoacoustics where you work on the trade-offs of your laser and work on your trade-offs of your sound. So light and sound together, that's how you work. So that's a whole new modality itself. Okay. Um, yeah, yes, the same principle follows. So the shift frequency here is can also be written as 2V cos theta F by, sorry. So now it's no longer your, this changes, but it changes due to your wavelength, the 2V cos theta by lambda. So this is your Doppler shift frequency, this is your velocity of blood flow, this is the angle in between the incident beam and the direction of motion, and this is the wavelength of light that you're trying to sample. Right? So this is your angle between incident beam and direction of motion. Okay, so with this we have covered all categories of kilometers. Only one which is remaining is this thermal based flow meter. So this one is remaining, but we have covered electromagnetic, sine, square, ultrasonic, transit, continuous pulse, and laser. Thermal flow meter is remaining. That like, and after I guess thermal flow meter, we also have respiration based measurements. So thermal based ones would be like something where you apply a constant voltage to it, and it will have a temperature difference across the points. It can also measure power in those cases. And similar cases, due to the change in them, the temperature difference, you'll get a flow of current there. Okay. So, of course, mechanisms there will change, but let's quickly look at the respiration-based measurement. We have different volumes, right? So, oh, sorry. So last time we looked at, like we saw that how your heart is pumping blood from one point to another point, right? So now here also, it's all based on your respiration volume. So, re- mm, respiration measurement. Yeah, there you go. So this literature is very well developed. You will see much more information on that. So try and avoid sources which are paid. I don't trust them as much. Please, we also have resources where you can look at that. And then you always have these learning platforms through which you can learn even if you don't want to take the course. I think that's good. But yeah, so whenever you're taking or taking some information from your source, like check the source of the information if it's true or not, and like you might have different things there. Oh, like this is something related to volumes. This is a simple one. I guess we should take this. It's from a publication in Springer, the 2017. This one, fixed it. So my tab does not allow me to write on images. So what I do is like I just highlight them and then you can look at the course material. You have these written very nicely. Like, I really like how it was mentioned. Okay. So when and how you need to do this respiratory measurements is something to assess the performance of your lung, how efficiently is able to purify your deoxygenated blood and is able to send the oxygenated blood back. You might have heard that some people do suffer from asthma. They suffer from like there are then asthma is typical one where like it's more common, where there are some conditions where you have pulmonary fibrosis. Like you'll have a point where in your lungs you have multiple fibers being developed, collagen being developed. Restrict themselves. They compress against themselves. They don't have enough oxygen in that particular point. So they die on themselves. So that's what happens when someone develops a lung cancer. Because fibrosis is the first stage for it. Okay. So there are different ways to measure the volume and the capacity of the lung. Our lungs can accommodate different volumes at different stages of the breathing cycle that we do. Fat points will inhale, will exhale. So how much volume is being kept in our lungs to a point, after a point, is what is being categorized. Okay. So the first one and simple one here is tidal volume. You can also call it as tidal volume, tidal volume. There are multiple names there. Of course, in British, Indian, and American English it varies. So that's tidal volume. Tidal volume tells you the amount of air that's being inhaled or exhaled during normal breathing, right? So this is the point where you are in normal breathing. You are resting in inspiring, you're resting in expiring, right? So that's what we are doing right now. So I'm talking with you. I am inspiring and expiring. So I'm inhaling, exhaling. So there's a normal amount of time. So I'm doing this process. So that's the amount of air that I have in my lung at a space where I can directly utilize it to the direct time, right? So that is called as tidal volume. It's approximately like 500 700 ml in adults, but kids and neonatal it's also much more less. Then you have the other one as inspiratory reserve volume. This one. So the extra air that you can inhale forcefully after a normal inhalation. At times you do this yoga. So what you do is like, okay, you'll inhale, but they tell you to inhale to the point where your stomach is getting filled up with the air, and then you stop inhaling. You place it after a time. So that's an extra amount of air that you can inhale after inhaling the normal inhalation. So that's what. So that's usually like in thousands, like 2000, 3000 ml. Then you have an expiratory reserve volume. That's the amount of air you can exhale forcefully, the extra air after a normal exhalation. So this one, opposite of each other. The amount of extra air that you can inhale after a normal inhalation, extra air that you can exhale after normal exhalation. So that's lesser because you cannot exhale more. Instead, you can inhale more. You can accommodate more capacity. You cannot exhale that capacity all in all. Then you have a residual volume. Residual volume is what's the amount of because now when you were trying to inhale forcefully, you had more amount of air. Whereas you're trying to exhale, you are not able to exhale forcefully amount of air which was inhaled in. So this is the amount of air which is left in the lungs after the maximum exhalation that you did. So this is like both of them equal to this, right? Then you have, so this will prevent your lung to collapse. Because if you exhale out everything, they will collapse, they will constrict themselves. Hence, you don't want that principle to happen. So that's how we all are made, and we don't know how this happens. Then you have different lung capacities, okay? So these are these capacities functions, right? So first is your inspiratory capacity. Inspiratory capacity is the amount of air that can be inhaled after normal exhale process, right? So your inspiratory capacity, so this one is nothing but from starts from this point, okay? Notice that particular point of interest. So that can be inhaled after your normal exhalation. So just if you look at this particular curve, everything to understand is relatively easy. So your inspiratory capacity can be given as what? It is tidal volume plus your inspiratory reserve volume, right? So it's the combination of both of them, right? Then you have a functional residual capacity. So this one at the bottom, this is your functional residual capacity. So this occurs if this happens in the tap. So this occurs when you have exhaled after a normal exhalation, right? So what's the amount of air remaining inside your lungs after a normal exhalation? So this is equal to your expiratory reserve volume plus your reserve volume. So no need to remember these terms. Just see the chart by yourself. You know that what this term stands for. One is forceful, one is after regular process. So that's how you can do. Then you have something called as vital capacity. Vital capacity is this one. So amount of air that a person can exhale after, so this is the maximum amount of air, vital capacity that a person can exhale after the maximum inhale. So this was the maximum, this was the inhalation after inhalation after a normal inhalation. This is the maximum inhalation. This is after which he exhaled, right? So this is given as vital capacity. So vital capacity is given as your expiratory reserve volume because it is after that particular point, plus your tidal volume because of a normal, and now this is your forceful, right? So this is your inspiratory reserve volume. This is how this process has been given. So this is now where is this used? We use vital capacity to assess the lung performance using using an instrument called as pyro. Look at its design. It's a really very cool thing. So what you do is like you have multiple walls in it, you blow air, and then you again blow air in between intervals, and what they do is like they measure. Back in the day, you also had a big box kind of thing. You go inside the box, you have a tube connecting, blow air in that tube after equal intervals time, and then there it is connected to the flow sensor from where you measure it further. Right. Then you have your total lung capacity. So this is the total. Maximum inspiration, maximum exhalation. Right? So this is the total amount of volume in your air after maximum inhalation process. So your total lung capacity is given by your inspiratory reserve volume, your tidal volume, your expiratory reserve volume, and your residual volume where you're trying to look. Okay. So this is all about your respiratory systems. This is the thing that I wanted you to look at. Now, there are different diseases associated when your lungs perform abnormally. Like if we won't do it, we won't have enough time for assignment, but let's restrict it here. So those things are like something as embolism where you develop bubbles in your head. So now these bubbles will cause interference and restriction to the blood flow. Will also develop acids. So that's nothing but change in medium. So your blood flow is being changing now. Your perfusion varies. Your carbon dioxide, oxygen, nitrogen, all levels in your blood will also vary. So that's a very likely if that happens, it's wrong. Then your airway can get obstructed. You don't have any ventilation. You have asthma. Then you have limited airflow. That's why person needs more amount of air to be inhaled at equal intervals of time. For because if he or her gets panicked, anxious, this gets adapted immunity. Then you have fibrosis. Fibrosis is something where you have the extracellular matrix or the collagen, your stromal components getting builded up, building it up. And they increase like the number density of them increases. So you have a very thickened membrane. Now, if you have thickened membrane, you always need an elastic membrane to pump blood in and out to get air oxygenated, deoxygenated. You need an elastic membrane which is thickened. It will get stiff. If it's stiff, it will affect the ventilation and perfusion cycle. Okay. So I hope we will be able to solve it. You can go online, look at the spirometer, how it looks like, and there are different sensors to it, and it also varies in between volume displacement, flow sensing, ultrasonic, and center phase sensors. So it's something which builds up upon the part that we have looked at it for now. I'm glad we were able to complete week three completely, and week four we have 2 points left, but we'll look at it later. There's also this, like you can after the spirometer, you can also look at new forgetting what it was called, new new tachometer. Okay, now this pneumotachometer is a type of spirometer which is like you measure the airflow in it when you are trying to breathe, but it looks cool. So you can also go take a look at spirometer, pneumotachometer. Just Google it, you'll see how it looks like. Okay. So quickly, let me know if you have any questions here. I'll wait for 2 minutes. Then I guess we have 3 minutes time. We can complete the assignment till then. Any questions? Let's see if it saves. Yes, it saves. I'll upload it and then how the session is completed. Very nice. Do you have any questions further? If not, then we can directly go into the assignments. Let's rename it quickly. You have or um, and then you have four. If no further questions, then let's begin with assignments. Here's the latest uploaded. Okay. So same thing, one question, and then we follow by 2 minutes for thinking time, and then we'll go with the answer for it or solution for it. Okay. The operating principle of an electromagnetic flow spectrometer is based on which of the following scientific laws? So here, tell me which law is it? Ohm's law, Coulomb's law, induction, Faraday's law of induction, Ampere's circuitual law. So just look at the name. So Ohm's law deals with something else. Coulomb's law also deals with something else. All are based on different principles. Probably Coulomb's and Ampere's circuitual law might be dealing with the same quantity, and Faraday's law deal with something else. Even if you tell me the quantities that they deal with, it's something you can directly answer the question. So look at the question more carefully. It's the principle of an electromagnetic spectrometer, where you have this term here. Okay. Any guesses?
Faraday law.
Okay, someone's trying to speak, but sorry, you weren't audible. Okay, so what's the operating principle of electromagnetic spectrometer? So this is Ohm's law. There's like voltage, current, resistance, Coulomb's law, current, induction law. Sorry. Mhm. Voltage, current, resistance, current, magnetic, or let's say induction, and perpetual law with the Ampere, so I'm not familiar with this one. Might be dealing with that. Okay, so not yet sure about this. Yeah. So we have Faraday's laws of induction. When the induction changes, when you have a magnetic field which is being applied, you can have a self-induction, you can have a mutual induction. So EMI, electromagnetic blood flow meters or blood flow sensors are based on Faraday's law of induction. Okay. Then next question. For continuous wave Doppler devices, typically they operate within which frequency range? So these are like their own operation frequency. So these are like the basic clinical based conventional Doppler systems. So they'll follow the lowest frequency as possible, but they remain within the clinical frequency range. So that is like 3 to 10 megahertz. Okay. So that's more of number range, but always remember what's the clinical frequency range for Doppler. That varies from like 3 to 15 or 20 megahertz. At max 20 megahertz, usually it's like 15 megahertz. And then if it's like high frequency based application like imaging eye doing ophthalmic application, imaging thumb doing like oral applications, for them you need a very high frequency. So then people deal with like 40 to 80 megahertz in those cases. Okay. So this is something which was not relevant to this question, but something to add it to your knowledge. Okay. Then, this we just looked at now, can answer it directly. Which of the following equations that represent the lung volume and capacity is not correct? So first is your vital capacity. Anything total. Oh, vital capacity is not that big, right? That was something else. Then inspiratory capacity. So we, sorry, is not correct. What was vital capacity? I think I'm confusing now. Let's open the no. Oh, let's open this one. Okay, let's see. We can probably do split screen here. Mm, and have this one open. That's cool, right? Okay. So you see vital capacity, where is vital capacity here? So it's like expiratory reserve volume, you have your tidal volume, and you have expiratory reserve for tidal volume, expiratory, inspiratory. So right, this is correct, right? Then you have so not correct answer for the question, but answer is correct. Then you have your inspiratory capacity. So where is inspiratory capacity? This is on top. So your tidal volume plus inspiratory reserve volume. So this is also correct, right? And then you have functional residual capacity. So this is functional residual capacity. So this is your vital capacity plus your residual volume. Can you call it like that? Your functional residual capacity has to deal with your reserve volumes. So after your exhalation, right? So you cannot, what do you have? Yes, exactly. So you cannot deal it with your, let's say what is total lung capacity. It's your vital capacity plus your residual volume. So that is also correct. How is, and then this is, oh, okay. I missed this term as RV. I thought this is RV, so hence I was looking at why is it. So your function residual capacity is what? Your expiratory reserve volume plus your residual volume, right? Not this one. This one. This one, if it was RV, then this was correct, right? So this is the option which is incorrect. All okay, not correct. So you need to go through this chart a couple of times to understand these relationships. Okay? But in exams also people do provide these charts. I don't know how the system for NPT works. I haven't taken this course or not given an exam for it. But when previously I gave, they did give charts for it. Or instead, if even if you don't have, these terms are very self-explanatory by themselves. So something as exhalation, inhalation, forceful inhalation. So you can always do it. Okay. Now, in an electromagnetic flow meter using a sine wave excitation, which type of current am I applying to generate the magnetic field? Is it a direct current, alternating current with a time varying magnetic field? Is a pulse DC current for precise sampling, or is it a static current to avoid noise interference? Which one? Any guesses? Like this, so I already wrote when I was looking, writing that okay, we apply a dash alternating something field so that we have it as a conductor through the vent and the magnetic field and voltage is induced like that. So you using a sine wave excitation, we apply a alternating current to generate a time varying magnetic field. Okay. Then in a Flesch pneumotachometer, so we didn't look at it really, or like we didn't go into depth of what the pneumotachometer. But let's see if we can directly see during the question. The pressure flow relationship is given by this. So you have P as equals to R and times flow rate. Considering the nature of airflow resistance, which of the following best describes the dependence of the resistance? So here on the side you have resistance, and here you have airway radius. So how it would be proportional to is what they are trying to ask. So this is your resistance, right? And times you have a flow rate here, right? So what is flow rate given by? Flow rate is velocity times area, right? Now area is something which is proportional to r squared, right? Velocity, it's distance by time. But this case you don't have so. And this side you have a pressure term, right? So how is it being related? What is pressure? Pressure is also related to force and area, right? How is pressure? Okay, how is pressure related to force and area? Right. Okay. We looked at this last week also. It's like force upon area, right? So you have an area component there also, and force has like mass and acceleration and electrical physical quantity, but here the force will be based on the gravitation and height differences. So you also have 1 by r square factor here, right? So because it's area, you have r square factor here. So your resistance can be written as, so if you do like resistance time velocity, if you take this r square down, you have 1 by r power 4 as your r and d. Your resistance is proportional to 1 by r power 4. Okay? So this is how it is. 1 by r power 4. So if you have basic knowledge, basic concepts, you can directly solve the questions. But of course, the physical phenomenon is also good. That's why I told you go and look at the pneumotachograph. Now, what is the approximate volume of anatomical dead space in a healthy adult during normal breathing? So this is like some volumes that are so of course the chart that I showed you only had those physical quantities, but you also have charts. So the first one that you looked at was with respect to the volumes that you have. So for a dead space, we usually keep as 150 ml, not 50 ml, it's very low. Our lungs will collapse at the point. It's 150 ml. Okay. Which of the following statements correctly describe the shift in oxygen hemoglobin dissociation curve? So this we haven't seen, but this is something associated with pulse oximeter. Okay, so how much oxygenated and deoxygenated blood goes in and down. That's how your pH changes. And now how it works is based on optical sensors. You send red and I guess it's a blue probably. Red and blue, two different types of lights. One which propagates or passes through our cells. So it has that quantity, that wavelength that it can pass through, get reflected back. The other one catches it. So red is associated with oxygenated and your blue is associated with the deoxygenated blood. So less amount of blood that you receive back is associated with decrease in pH, but more and higher in rich is like more in pH, and not more in pH. So you're basic in pH. So that's how you deal with it. So our questions are, so which one correctly describes? So let's see. A decrease in pH or an increase in temperature shifts the curve to the left. Okay. So it's telling us that a pH is decreasing and our temperature is increasing. So that will shift the curve towards left. Okay. Increase in pH, a decrease in temperature will shift the curve to the right. Okay. So what you're trying to look at, what are the axes for this oxygen hemoglobin dissociation curve? Let's look at it. Even if I'm not recalling it correctly. Oxygen dissociation curve. So, okay, so in this one, what we look at is the percent saturation, and we look at the pressure. Okay, and then a decrease in pH or an increase in temperature will cause it to shift to right. Well, this is not possible. I yeah. And then an increase in temperature or decrease in pH has no effect. Well, this is not true. Will have no effect because it will essentially shift. So the amount of shifting towards the right tells us that at higher pressure the blood is getting oxygenated or getting saturated. At lower pressures, it's not. It's only increasing at that point. So let's see. So decrease in pH and an increase in temperature will shift the curve to the left. So if we are shifting to the left, lesser lower pressure, so we're talking about higher saturation, saturation which is increasing. So if my saturation is increasing, my pH cannot decrease. This is cross. Increasing pH or decreasing temperature will shift the curves towards right. Well, this was right because my pH is increasing, my temperature is also shifting down because my pressure is now increasing. So it will shift the curve towards the right. A decrease in pH or an increase in temperature shift. A decrease in pH or an increase in temperature shift will shift the curve towards the right. Of course, your pressure and temperature cannot do it. Okay. Of course, next time when we begin the session, do remember me that we first start with the dissociation curve and give you a brief introduction on it, and then only we'll move ahead. Then again about the fish new tachometer that which measures the airflow based on the pressure drop across resistance, and then it operates on which physical principle. So what is that principle being called? So it's like Paul's law, Paul's law of flow. Okay. It's that. Then in thermodilution technique, so we didn't see about thermosensors. Let's see. What is injected into the bloodstream to calculate the cardiac output? How? What do we inject in the blood? Like we cannot like even inject anything in the blood. We inject radioactive traces when we do PET scanning. So that's a type of imaging. We also have its own half-life times. It's like people don't prefer it. It causes harm to ourselves because it implies carbon dioxide. We won't inject, right? Oxygen can be injected, but that's at later stages, like when we need oxygen. So we only inject the whole thing. Like even if you don't know the concept about it, I'm trying to tell you in a form that okay, you can attempt the question in a way you look at the technique and what's being like what is being done currently. So you might have knowledge about that. Okay. Arterial stenosis, particularly which involves the aortic valve, right? It refers to which of the following. So what happens in arterial stenosis? It's something where so stenosis, stenosis, these are like similar walking terms. What you do is like your arteries they collapse it. So in a way you can say that your valves are getting constricted and you don't have enough blood flow through it. So can be dilation because it's flowing. So stenosis is a term related to lesser constricted like that. It's constriction of the valve, right? And inflammation of pulmonary node because we're only talking about arteries, aorta. Blockage of coronary artery due to fat deposit. This is some other kind of disease. Also look what this is called. So this acid is constriction of the aortic valve. Okay. So with that, we are complete with the assignment for this week. That was a long one. So if you have any questions, you can let me know now, or else we can always discuss whenever we meet next. You also have the discussion forum to put your questions in. If you have any further questions next time also you can ask me. Now is also the time to ask me. So as and how you comfortable. Any questions? Of course, I covered the pneumatachometer and the oxygen saturation dissociation curve in the next week. Then we'll be and this thing you'll get it on the sheet that's been shared with all of you. And you'll also have this lecture notes and assignments attached in that particular sheet. So there's this one OneDrive folder that I have, and I keep updating it. So you'll have those things attached in there. You can always go have a look on them. And even if I make some mistakes, you can always let me know. We can also interact and discuss about it and can clarify afterwards. Any questions? Okay, so I got two thumbs. Okay. So no more further questions. Then thanks for attending today. Sorry for disturbing you on Sunday morning. Have a very nice Sunday. Thank you for attending. Bye bye. Take care. Oh yes, yes. You have any questions? You can go ahead. You can unmute yourself. At the Any question? Oh, I guess you. Oh, okay, works well for them. Okay then. Thank
No,
you. Thank
ma'am.
you for. You have something? I can't hear you. Can you try speaking again? You can perhaps connect your audio to Teams. That way you can speak up.
No, ma'am. We did not have doubt.
You Uh, I guess what we'll do is I'll post this on YouTube. Your question you can post it there. Okay. I'm not able to hear you, and I guess within 2 minutes this meeting will also complete it. So I won't be able to interact with you more than that time. And then we're also meeting on this 18th, so that's also next Tuesday. If you have other questions, we can discuss it then. Okay. And also you can post it on YouTube. I'll be very quick in responding there also. If not, on discussion forum also, you have multiple TAs like me, so they'll also respond you as soon as they can. Then thanks for attending today. Thanks for being here. I hope this was a nice and good discussion session forum that we had. Thank you. Bye bye.